Welcome back, physics. Today we are going to be talking about the conservation of momentum. But before we really discuss that, I want us to remember our answers to the last part of the impulse and momentum notes. Please pull out your notes for conservation of momentum as well, as I will be giving you the fill-ins for the blanks. All right. So remember that we had this bus that was driving towards a bug, and we had the first three answers, which are important to understanding the conservation of momentum. So first, it was asked about which object is applying a greater force. It was asking about the bug, if I remember correctly. But because of Newton's third law, right, if there is some force, right, if they collide, there's some force being applied here. Well, then when I see the reaction force, it's going to be the same size. And I'm going to use this dash to represent the same length. So we see they have the same force. Okay. Change my color here so it's a little more clear. And we also mentioned that the time of the collision, so the time of the collision for the bug is equal to the time of the collision of the bus, right? As long as one force, the action force, is being applied, the reaction force is still going to be reacting. But once we get rid of that action force, well, then the reaction force is also going to disappear. So if we wanted to find out who created a larger impulse, well, that ends up being the same again, because impulse is equal to force times time, right? So if force and time of both of the interactions are equal to each other, well, then impulse is also going to be the same. So we mentioned that the force is the same, that the time of the impact is the same, and also the impulse is the same. And this is really important because it means that our change in momentum is also going to be the same. Since the impulse momentum theorem tells us that impulse is equal to change in momentum. Now, why are these answers important? Why do we care? Well, if the momentums, even though they're different, if the change in momentum is the same, then that means that whatever the bus is going to lose, the bug is going to gain. So the more significant takeaway is that whatever momentum is lost by one object, the other one is going to gain it. So let's scoot this over a little bit so we can write down some things. And so we used Newton's third law to come up with this, right? Newton's third law. For every action, there is an equal and opposite reaction. And so this tells us anytime there is a net force, then we have a momentum transfer, right? If I push against you and you start to move, well, then I have transferred some momentum to you. So this is confusing on a conceptual level. So let's bring it to something that we understand a little bit more. Let's deal with some money. So let's say you have $20 in your pocket. Okay, you're at school. Let's say it's normal time. And your friend asks you for $5 to buy Chick-fil-A for lunch, right? It's $5 for the chicken sandwich. And you're a generous person, so you give it to them. So, right, if you want to know how much you have left over, you subtract the $5, you now have 15. Now, Mr. Z, you might be asking, I have less money than I had before. That's true. But you and your friend together still have the $20, right? You have 15, but he's got the remaining 5 to make up the 20. So now it's not just you with your dollars, right? It's you plus your friend who's got the remaining amount. And so both U together gives you the $20 again. Now, even if your friend transfers this to the vendor outside, right? Now they're going to have the $5 and your friend no longer has any, right? We'll put a hat on them to represent Chick-fil-A. I'm not going to draw the chicken because I can't draw. So now the vendor has $5. And so still all together in this system of people, there's still the $20 at the end. In physics, we call this a system. And this is important because we want to consider the things that are interacting with what was initially there. So thinking back to our bus and bug, right? We don't consider a lot of things. We just consider the bus and we just consider the bug in the system because those are the two objects that are interacting, right? Initially, it was just you and your friend, but we had to expand the system now to contain the vendor, right? And even once the vendor brings it back to Chick-fil-A, they put it in the bank, right? The $20 is still there. It doesn't go anywhere. Now, money is more complicated than that, obviously, so we're keeping it simple. This is where the analogy breaks down. The same thing happens with momentum. So let's bring in our bus and bug back here. So let's say that the momentum of the bus is equal to 100 Newton seconds. Okay, and the bug is going to have a momentum of, let's say it's 1, right? Let's say it's got a momentum of 1. We'll give it dummy numbers. Okay, Newton seconds. Okay. So right now, right, we've mentioned that in the past, the momentums of the bus and the bug are obviously different. They're very different. They're not the same. But the transfer of momentum is going to be the same. So let's say that in the interaction, the bug receives has a change in momentum of, let's say, 10. Okay, 10 Newton seconds. So the final momentum of the bug final, it's going to be 11 Newton seconds. And the bus is also going to have a change in momentum, but it's going to be the opposite, right? Negative 10. So the momentum of the bus final is going to be 90 Newton seconds. So this is how it works out conceptually. And if Newton's third law holds, well, we'll see this happen as long as this system is isolated. If there are other systems or other objects at play here, then we're going to have a different transfer of momentum. We'll have to consider other objects interacting. So there are two kinds of collisions. There are elastic collisions and inelastic collisions. And you are going to be investigating if the conservation of momentum holds up for each of these.